Welcome once again to tutorial on the BJTs, and today in this tutorial video we're basically going to learn about the load line analysis. Okay, but before we move on to the details of this topic, let's just first consider this particular circuit diagram where we can see clearly that it's an NPN type of a BJT. Okay, I'm going to write it down over here. So there's an NPN type BJT used over here, which has been configured in the CE mode of operation. Okay. If you all will remember from the previous tutorial where I just said that, from now on we're basically going to use the CE mode for all sorts of transistor-based operations, since it is the perfect one suited for amplifier-oriented operations as concerned. Okay, so the load line analysis that we're going to talk about over here basically becomes very important when we basically try to make an amplifier out of a BJT. Okay, so now the BJT, it has been optimized as an amplification type of device, and that's why in order to use the BJT as an amplifier, we need to perform certain analysis, out of which the load line analysis is the the foremost important thing that we need to do. So if we would care to take a look at the characteristics of this particular BJT concerned, there you go, that's its characteristic curve, and that's the output characteristic to be precise. Okay, so now why did I went on to show you the output characteristics of this particular BJT? Okay, so this is basically done in order to give you an idea about the load line analysis, which we are going to learn over here. Okay, so before we go on to load line analysis, if you would carefully take a look at the output loop of this particular BJT, you can see that there is a voltage source VCC that is basically biasing the collector junction. Okay, reverse biasing the collector junction, and then we have this particular resistor over here known as RC, also known as the collector resistor. So here RC, that we are basically calling it, is basically known as the collector resistor. Okay, alright, so there you go. Fine. So in this particular output loop over here, you can see that the circuit is complete, and the input over here is already being forward biased. The emitter junction has already been forward biased with this particular bias voltage source, that's VBB over here in the input part of the BJT circuit. So considering that this particular BJT would operate in the active region of operation, and that its input junction, that's the emitter junction, has already been forward biased, so the most obvious thing that would or rather that we might come across in its output loop will be that there would be a collector current that would flow in the output loop due to a corresponding input base current that would probably enter into this BJT through the base terminal over here. Okay, and now this particular voltage source, since it biases the emitter junction in the forward direction, so that's why the BJT is just in its conducting state. Okay, so assuming that it operates in the active region of operation, okay, we can just basically we can just write down an equation for the output loop of this particular circuit using KVL. So if we would just pull the page down a bit, okay, so if we would apply KVL over here, then probably we can get the output loop equation as VCC equals to, okay, let's just take a look again. Okay, so you can see over here that this particular voltage source gives us the entire voltage supply for the output loop of this particular circuit. Now a part of this total voltage would appear across the resistor RC right over here, and the other remaining part would appear across the collector and emitter terminals of this particular BJT. So if I might write this one as, let's say, VCE, that's the collector to emitter voltage that would occur across the collector and the emitter terminals of this particular BJT. Okay, so we can also quite easily understand that due to the flow of this particular collector current through the resistor RC over here, it would cause a voltage drop of about, well, RCIC. Okay, or rather it's better if I write it in the reverse way, so it would be, well, ICRC. Okay, that's better. So this particular voltage drop across that of the resistor RC and the voltage drop VCE across the BJT's collector and emitter terminals, when they are just taken together as a sum, then it should be equal to the total voltage supply provided from the biasing voltage source. So from KVL, or rather I might write it down over here. So from KVL, we're basically going to get this for the output loop. So VCC would be equals to, well, VCE plus that of ICRC. Okay, so let's just call this one as, well, equation 1. There you go. And now, if we're just going back into load line analysis once again, so now if we just talk about it, then let me just tell you, load line analysis is probably a method of, well, determining the corresponding collector current, determining a particular collector current and its corresponding collector to emitter voltage for a particular BJT. Sounds confusing, right? Okay, so let's just come back to the circuit once more. You can see that for a given collector current that's just going to flow through the output loop of this particular BJT circuit, there would be a corresponding voltage drop across the collector and emitter terminals of this particular BJT, which we just call the collector to emitter voltage. Note that this particular supply voltage, that's the VCC over here, is not variable anymore. It's just a constant voltage source. So for a given particular amount of voltage source being applied to reverse bias the collector junction over here, for a particular value of collector current drawn by the BJT, there would always be a corresponding collector to emitter voltage drop occurring across its collector and emitter terminals. Okay, so often it's quite necessary to, well, determine how much a voltage would occur across the collector and emitter terminals of BJT for a given value of collector current. Well, in those particular cases, how do we know that, or rather how do we determine the particular values of the collector to emitter voltage, or rather the collector current? Then comes the load line analysis. Okay, so if we just take a look over here once again, then if we just take a look at this particular equation, well, we can just get to understand that the voltage coming from the supply voltage source just divides itself into in two parts and distributes across the resistor and the BJT's collector and emitter terminals. Now what I'm just trying to say over here is, if we would just well, for instance, if we would just keep the input if we just would keep the input open circuited, so that the bias voltage source VBB is not connected to the base terminal anymore, then it's quite clear that we wouldn't have any sort of forward bias voltage drop occurring across the emitter junction over here. So as a result, the BJT would be, well, sent into its cutoff region. So and there won't be any sort of input base current as such. So since there's no input base current right now, there won't be any sort of collector current flowing at the output loop as well. Why that's so? It's because if we just take its output equation once more, if we just try and remember it as I had shown you in the previous tutorial, that the output equation for the CE mode would be given by, well, IC equals to, well, about beta IB plus that of ICEO. Now ICEO being the the leakage current over here, it's quite small in magnitude. We can just ignore this part out of here, and for the quick evaluation purposes we can just approximately take the equation as IC approximately equals to beta IB. So we can just see over here that the collector current depends upon the input base current over here. So if the input loop is just open circuited, there won't be any sort of input base current, so as a result collector current would be 0. So under this particular circumstances, the BJT's emitter junction being reverse biased, or rather having no forward bias applied across its the base and emitter terminals, the BJT's just becomes an open circuited circuit element. Okay, So during that time, what happens is that the entire voltage drop coming from the voltage source VCC that's connected at the output loop would be obtained. I mean, entire voltage drop of this particular voltage source, that's VCC, would be obtained across the BJT's collector and emitter terminal. So under this situation, what happens is that, if I might write it down over here, so if IC equals to 0, then in that case, well, the entire collector to emitter voltage will be equal to that of the voltage coming from the voltage source, so the entire voltage coming from the voltage source. And once again, if we would just, well, connect the open circuited input loop once again and let flow the maximum amount of base current that is that the BJT could tolerate. So I'm just writing it down as IB equals IB max. So under this sort of a situation, the collector current would be, I mean the BJT would just be driven into the saturation region, and the collector current would be maximum as well. So we'll have a collector current of, well, IC equals to IC max, or rather we can just write it down as IC sat, which means IC saturation. Okay, so under this sort of a situation, what will happen is that the BJT being forward biased, it's it'll just be it'll just provide a continuous path for the current to flow through itself. So it just becomes a shorted circuit component right now. So what happens is that the entire voltage drop would just occur across the RC resistor connected right over here. So the voltage drop across that of the RC resistor right now, when IC is equals to, well, IC sat, at that moment the entire voltage drop across that of the the RC resistor, if I might write it as, well, VRC, okay, so that particular voltage drop would be just equal to that of the the voltage, entire voltage coming from the reverse bias voltage source VCC. And under this sort of a scenario, this particular phenomena would occur because the BJT just behaves as a shorted circuit component. Okay, so these conditions that I'm just gonna I just discussed over here are the two basic characteristics which we can just obtain at the two extremities of the load line. So I'm just gonna show you how we can just obtain that. So if you just care to put all these conditions right in equation 1, okay, so let's just put in equation 1 IC equals to 0, and let's see what we get for VCC. If we just this particular condition, if we just treat this as condition A and the other one is condition B, so if we would put IC equals to 0 in equation 1, then we are going to get the condition A right over here. Because if we just open circuit the input part of the circuit, input loop of the BJT circuit up there, then there will be no collector current. So if we just put IC equals to 0 in this particular equation, then we're going to get this particular condition, that's condition A over here. So under IC equals to 0, if we might write it down over here, so VCC, there you go, VCE plus, if we put 0 in the place of IC, then it's quite natural that the ICRC term would just vanish. So it's quite obvious. So under that sort of situation, we're going to get, well, VCC equals to VCE. So that's how we obtain condition A. And as per condition B is concerned, if we're going to put, well, IC equals to IC sat, then as I had said back then, that the entire voltage drop coming from, entire voltage of this particular biasing voltage source would just drop across this particular resistor RC, so that the entire voltage drop across the resistor RC would equal that of the entire voltage drop of the voltage source, the reverse biasing voltage source VCC connected in the output loop. And at that moment, the collector emitter voltage would just be equal to 0. So if we would just put this particular condition in equation 1, then for okay, let's just write it down over here. So for VCE equals to 0, if we just put VCE equals to 0 over here, or rather I might write it down this way, that well, we have ICRC, okay, yeah, there you go. And if we have the VCE equals to 0 for IC equals IC sat, okay, if that's the condition, then if we just eliminate the 0 mark from over here, then it's quite natural that for IC equals to IC sat, VCC would just be nothing but equals to that of the voltage drop across that of the RC resistor. So we can see that from this particular equation obtained from KVL, we can just get equation, I mean we can get condition A and B both. And now if we would just care to plot this, the conditions obtained in condition A and B in the output characteristics of this particular BJT, then in that case we would be obtaining the load line. Okay, so if we would take a look at the conditions A and B once more, then we can see that, well, IC versus VCE, I mean we have corresponding points of IC and VCE. So if we just care to put condition A in if we just care to plot this particular condition A in the output characteristics over here, we can see that from condition A, IC is equals to 0 and VCE is equals to VCC. So over here, as we know that VCE is equals to VCC, let's just assume that, well, this particular somewhere over here we have the point. I'm just going to pull it down and write it over here. So let's say that somewhere over here we have the point VCC that just represents the magnitude of this supply voltage source. And for for IC equals to 0, we have VCE equals to VCC. So this is the very first point that we're going to get right over here. Okay, and if we just care to plot the condition B also, then we can see that for VCE equals to 0, the current IC is equals to IC sat. Okay, so the point VCE equals to 0 is over here, and corresponding to that, let's say this particular point right over here represent, well, IC sat. So let's say this represents IC sat. Okay, and now if we would just care to join these two points with each other, okay, so let's just join them. All right, bingo. Now joining these two points, we obtain what we know, or rather call, as the load line. So this particular line that we have over here is the DC load line which we were talking about. All right, so this particular load line is can be mathematically defined as the locus of all the corresponding collector current and the collector to emitter voltage points in the output characteristics of a particular BJT circuit. Okay, so we can use this particular load line in order to determine the exact values of corresponding collector to emitter voltages for given values of collector currents. So that just makes analysis easier. All right, now if you would also notice over here that with the output curves that you have in the output characteristics of this particular BJT, the DC load line intersects with them at these particular points. We'll just call them, well, somewhat Q1. Okay, we'll just call them Q2. Also we can call them over here as Q3, Q4, and this one over here as, let's say, Q5. So as you can see over here, these points that just denoted with the symbol Q are the points where the load line, the DC load line, just intersects with the output curves for different values of base currents. Okay, so now these particular points with which the of the transistor output curves with which the DC load line intersects represent the various Q points, or the operating points. Okay, so we will just basically call them as operating points. Okay, operating points or Q points. Okay, they're also popularly known as Q points. So these are the particular points where we need to keep the transistor, or rather the BJT, biased, so that we have a particular value. Let's say if we just consider a Q2 over here, if we just plan to keep this BJT over here biased at this point, Q2, then we would need to provide a particular, let's say we need to provide this particular collector to emitter voltage. Let's just call this one as well, VCE1. So then we need to put the collector to emitter voltage as VCE1, and the corresponding collector current would just then be given by, well, let's say IC1. So for if we just need to, well, keep the BJT biased at this particular Q point Q2 over here, then we need to keep the collector to emitter voltage of this particular BJT output circuit at VCE1, and correspondingly the collector current would be IC1. Okay, so these are the necessary conditions. So we can make the BJT operate in any of the operating points that we can see over here, and correspondingly we'll be needing to keep a particular value of the collector to emitter voltage and also the collector current corresponding to each of these operating points, and that's why they are so useful, and they just comes from the load line analysis. Okay, so that said, we just wrap up our discussion over here for now. And don't just forget to watch our next tutorials, where we'll be showing you how you can just learn about the various types of amplifiers that can be constructed using a BJT. So till then, it's just going to be a short goodbye for now, and thanks for watching.